this video, I want to start our discussion of three-dimensional rigid body kinetics. And to consider rigid body motion in 3 dimensions, there's a few things that we have to modify from what we've seen before and apply them in slightly different ways. So to start with, I want to revisit our equations of motion for a rigid body, for which we might have forces applied in various directions and get a resulting linear acceleration out of that. And we might apply moments and get some resulting rotation. Now, the second equation probably looks a little different from what we've usually expressed it as in the past. And here I'm writing the equation in terms of the angular momentum, where we've previously defined the angular momentum as I omega. Now, of course, we can see that the derivative of I omega would be I alpha, and that's what's indicated by the dot here to kind of take into account that we're taking the derivative of the angular momentum. So for a rigid body with some center of gravity location, representing this graphically now, we might have some linear translation represented with the acceleration a, and we might have some angular momentum represented with h there, h dot. Now, when it comes to applying this scenario to three-dimensional rigid bodies, this definition of angular momentum here is not quite accurately applied in that there's some assumptions built into it based on symmetry that we need to work through. So this definition for angular momentum needs to be changed. So to do that, to take another look at the angular momentum, we're going to take the angular momentum and represent it as a vector. With components in our 3 Cartesian directions. And to do this then, we're going to break up the inertia here, the inertial term, and represent it in terms of all the possible components that it might contain. So the first terms that I'm putting in here look relatively familiar. We could think about the inertia of our rigid body with respect to our 3 coordinate axes, x, y, and z. However, because this is we're talking about 3-dimensional rigid bodies that maybe aren't necessarily symmetric and have some other things going on, we need to also take into account the inertia, or what are called the products of inertia, which is a consideration of the rotation or the inertia of the rigid body with respect to one axis while it's rotating around a different axis. So, for example, if I include the inertia xy here, I'm talking then about the inertia of the rigid body with respect to the y-axis while the rigid body is rotating around the x-axis. So it's a taking into account these different orthogonal planes. And as a result of how we define inertia, we have a negative sign on here in terms of how it would contribute to the overall inertia, or how it would contribute to the overall angular momentum vector. So the other thing to note is that because this is a symmetric tensor, this term has an equal term on the opposite side, which I would call ix or iyx. However, it's going to have the same value as ixy. So there is symmetry across this tensor. So I can fill in the rest of my tensor with the remaining terms. in that form. Now to complete the vector definition, we need to express a vector formation of the angular velocity. So as I've already described it a bit, this middle term here is called the inertia tensor. And it again defines the different ways in which we might consider our rigid body undergoing various forms of rotation, or maybe able to handle various forms of rotation would be a better way to say it, and being able to account for a wide variety of geometries, not necessarily symmetric about any one axis, and kind of a more general approach. Now just to kind of spell everything out, we can expand the matrix multiplication of this to kind of see what the individual equations would look like. So if I carry out a matrix multiplication, multiplying the top row by the one column of my angular velocity, so once it's fully filled in, I get three equations, one for each of my vector components of my angular momentum. Now within these equations, we need to think about how the various components, moments of inertia and products of inertia are defined. So in order to be able to define what these quantities are, these inertial quantities, I want to think about this in terms of my coordinate system. So I'm going to put a three-dimensional coordinate axis on here, and I'm going to consider any given spot or location of some mass. So we'll say that this is some differential unit of mass where the location of this mass is defined by some measurements x, y, and z. And so as I start to define the moments of inertia, ix, iy, and iz, I need to think about the distance corresponding to that particular location. So if I'm talking about ix, I'm talking about the distance to the x-axis. And I want the shortest distance between those two. So that's the perpendicular distance to the x-axis. And we can see that this triangle would define that distance, and it would give me y squared plus z squared. And the same thing would be true for the distance to the y-axis, as well as the distance to the z-axis. So if I go ahead and write those out, I would take the integral of all of the various distances for all of the mass in my rigid body. Again, I've only drawn here a single differential unit of mass, but if my rigid body is some shape around this, each little spot within that rigid body has some differential unit of mass. And so I would integrate in order to sum those all up. So I would get an equation of the form like this for x, and similar equations for my remaining moments of inertia. Now, to define my products of inertia, I need to think about what I'm actually talking about here. So for the products of inertia, I'm looking for the distances to the corresponding planes. So, for example, if I'm looking for For example, if I'm looking for the inertial element xy, I'm interested in the distance to the yz plane, which would correspond to x, and I'm looking for the distance to the xz plane, which would correspond with y. So therefore, I would pull those two and get them together as of the form xy is the integration of xy dm. Now we should note, however, and I should have wrote this in here, is that ixy is equal to iyx. Again, that inertia tensor has symmetry, so we can say that both of those things are equal to each other. Similarly, iyz is equal to izy. And now I've got my inertia tensor fully specified in terms of how I might compute that using these integrations. Now, as you can probably see, this gets messy very quickly, and the products of inertia kind of are a little bit difficult to work with and to understand. One of the things that we would note about, for example, the moments of inertia is that they're always going to be positive values, right? These squares on each of these terms indicate that these are always going to be positive inertia values. With our products of inertia, that no such rule applies, and we can have negative inertial quantities here, and it all just gets very complicated. So in the next video, we're going to talk about a simplification of this that makes our life a little easier and makes these a little bit easier to work with. All right, thank you.